My name is Mike. I'm one of your volunteers here. We have several other volunteers in the room. And tonight we have actually two special visitors here. We have our speaker for tonight, Suzanne Metlay, professor of astronomy at Front Range Community College and outreach director in her past life at the Fisk Planetarium and all kinds of other wild assignments that she did. She will be our speaker for tonight. But we also have Chad Wright out here, the original founder of this observatory. So we'd like to get... He is here visiting his son Bale, who is performing in the Central City Opera as a baritone or tenor. Tenor, okay. So maybe you can do some tunes here tonight.
I'll always give the floor to you.
So Chet, why don't you come up here for a second? Chet was the earth science and astronomy teacher at the high school for many, many moons and many moons ago. Many moons ago. And he was one of the original 3 or 4 people, I think, that started this whole idea in 1996, 1997, 1998, somewhere there, when he had a little more hair and I didn't have as many gray hair. He's also responsible for our beautiful constellation wall for any rainy nights. We didn't have that before. Right?
Yeah, no rain.
Maybe Chad wants to relay some of the old stories on the observatory here.
I was working on a project with Tom Patterson, and he was a teacher in our school. And we got a call from Tom Melsheimer saying that he thought it would be a neat thing to put an observatory on the campus, and we thought also that would be a great idea. And it developed from there. The original building, complete with dome and telescope and everything, was done for a cost of $50,000. And the reason that it was that cheap is we had so many businesses that helped us out.
And lots of students, right?
Lots of
slave
students.
labor. Yes.
Oh, slave labor on that wall, yeah. What I did on the wall is to project a map that came out in Sky and Telescope magazine. And then I did a little research to figure out which stars are which colors. And so that's fairly accurate as far as magnitude and color on the stars and on placement. And you notice that we've got the north projection, which is for the northernmost constellations that sort of bleed off the top here. In any case, this has been a tremendous facility, and it's just really exciting to come back here and to see the new telescope. I'm trying to talk Mike into aiming that at something so that we can actually see some light through it tonight. But I'm not sure if that's going to happen. But
we'll do our best.
Certainly with the 18-inch and the wonderful 6-inch refractor, which I understand this gentleman here has provided us with, we've really got a wonderful facility. So, just wanted to say that I am very impressed with what's taking place. Scott Kent, of course, raise your hand there, Scott. He's not only taken over my astronomy classes, but just to blend in, he's lost most of his hair also. But then again, maybe it's high school teaching that does that, but I'm not sure. But I'll turn the show over to you. Thanks.
Thank you, Chad. When did you retire, Chad?
2004.
2004, so you've been gone since then. Chad now lives in Port Townsend, Washington State, up on the Olympic Peninsula. Nice place. He bought a very large seagoing kayak, 2-seater kayak, and takes multi-day, multi-week kayak trips. So he loves life. He's also a recumbent bicycle
Yeah.
Not? Whatever. But anyway, we enjoyed working with him early on, and we were glad that he came back to visit us here tonight. Anyway, tonight we have Suzanne. Are you ready for your talk?
Yeah, whenever you want.
Okay, can you highlight the talk a little bit more? I mean, I only know is that it is about time, and time and space is a little different, right?
Just a little bit, but I'll get into the details later. I wanted to thank everyone for coming out tonight. It is a beautiful night. We do have more chairs, so if you don't mind filling in the center so that people can sit down along the edges, that would be helpful. Because it'd be great if everyone could sit down tonight. So thank you, members of the Birth and Community, for coming out. Thank you, members of my classes at Front Range Community College, for coming out. I appreciate that. And I'll do my best not to bore you. We're waiting for the clouds to go away so we can actually look through telescopes. So we'll see if the winds shift the clouds so that we can actually get some good viewing out of these great telescopes. Yes?
I was able to line the scope up. I was able to see a couple stars. So I bet in an hour or so we'll have a really good viewing.
Excellent. So I will keep it to definitely under an hour. Don't worry about that. I've had the privilege of speaking here every June for many years, and I will keep coming back as long as Angie is cool enough to keep inviting me. So thank you. And I really love the fact that everything here is donated by volunteers. Handmade, hand refurbished. That Mount Wilson telescope that Chet was talking about came with, what, a bird's nest in it or something? I mean, it's just, and it's been lovingly put back into use. So that's why it's taking a while, because no one's getting paid to do it. It's all volunteer effort. And so you guys are a fantastic community for supporting the work and doing the work. So thank you guys.
So Suzanne, for the first time, I think we have cooling now in the summer.
Wow.
Right? I mean, every June you were kind of...
It's a little warm in here
hot house,
sometimes.
right?
Yeah, that's great. Congratulations. So every year it's improved. Great. Okay. Well, I think it's time to actually get started. What do you think? Okay. So the question is, what time is it anyway? Because it turns out when you start trying to think about how do you tell time and what's going on, it actually gets really complex really fast. And there's no way we're going to cover everything tonight, but I thought I'd give you some basics. And the very first one is the world going to end? And the answer is no, and the Mayans themselves said no. Ignore that round, long-form calendar you've all seen on the internet. Just a few months ago, it hit the news that there was a hidden building in Xultun, Guatemala. Hopefully I'm pronouncing that right. And this is the original. And this is, once they cleaned it up and did some analysis, what they think it was. A Mayan ruler, obviously a king, with his blue feathered headdress and his white scepter, and in the other hand, other symbols. He even has a servant hiding behind his chair here. So you know this is a big, powerful guy. And along another wall was an image of a scribe, someone who kept the calendars and the records. And one of the calendars was this, and this at the top, again, is the original. And it doesn't look like much of anything. But then you realize, wait, those are dots, those are dashes. Hang on, this is writing. And the writing is actually the lunar calendar. This was from about 1,200 years ago, about 800 years into our modern era. And here's the important part. They correlated movements of the sun, meaning years, just like our regular calendars, movements of the moon, and then Venus, and then Mars. And they didn't do this for just a few cycles. They did this for 17 Bakhtun, which turns out to be about 3,500 years. So if you take 1,200 years ago, and then you take it up, okay, the world's not going to your own calendar says so. We're going to keep going for quite a while. It depends which calendar you look at. Do you look at the one, you know, from the one where you peel off a joke a day, or are you looking at the longer perpetual calendar kind of thing? This was obviously a longer long-form calendar. So, hey, we're fine, chill. December 21st, 2012 is going to be interesting all by itself for another reason. Anybody know what astronomical event is going to take place then? What was that? Not equinox. Solstice. It's going to be winter solstice. So that'll be cool. So let's go back to talking about how we relate time to place when we talk about the moon and the sun. When we look at the moon, believe it or not, you're looking at a timekeeping device. And my Astronomy 101 students have had their faces dragged through this, because I make them figure out what time it is based on the phase of the moon. And you can tell that, in fact, I'm going to have one of you shout out, please. What is a moon phase? Come on. Yes. Thank you very much. It's how much sunlight is reflecting off the face of the moon. And that's all a moon phase is. Because we always see the same face of the moon. The moon has synchronous rotation with Earth. We always see the same face. But look, sometimes it's lit up from the left. Sometimes it's lit up from the right. That means sometimes the moon is in the sky ahead of the sun. And sometimes the sun comes in the sky first and then the moon follows. Sometimes we see it all lit up, sometimes just a little bit. And you can actually tell what time of day it is, even if the sun has set, just by looking at the phase of the moon. And of course our ancestors did this, and they didn't need to get college credit for it. They just knew how to do it. Now this is really interesting. Has anyone ever seen a picture of this before? This is called the Ishango bone. And it was found in Central Africa. It's dated, we think, to more than 20,000 years ago. And you see these vertical cuts? Somebody's keeping track of something. And we think it's moon phases. Now, this could have been, again, a scribe in a temple, just like I showed you earlier. It could have been a woman keeping track. Could be all sorts of things. So we don't know who carved it, we don't know why, but we do know that it matches perfectly to lunar cycles. So 20,000 years ago, humans were keeping track of time. They were building calendars. Here's another calendar. And again, Astronomy 101 students, what's this called? Analemma. And this particular image was taken by Anthony Iomamadis in Greece. So this is a real Greek ruin. This is the real analemma. He set up his camera and he kept it stationary for a year. And every day at local noon, he took a picture. Now this isn't every day out of the year, because that would mean 365 points. So he just picked the good ones. But this really is the pattern that the sun makes in the sky. And remember, if you're from a traditional culture, you think the Earth doesn't move, it just stands there. And the sun goes around the Earth, then you go, wait, what's this? So, what do you think this tells us? Say that again, please. It is the seasons. Excellent. So, this tells us actually why winter solstice, December 21st or so, why we experience what we experience. The sun literally doesn't get very high before it starts to set again. On the other hand, at the very top, we've got the summer solstice. Look how high that is. Well, do you guys know when is our summer solstice? Well, actually, this year it's June 20. So on June 20, our sun, from our perspective, is going to get as high in the sky as it ever gets, and it's going to seem to hover. It's going to seem to stay there forever. Well, of course, that gives us a longer day. That's more time for the land and the water to heat up, and that's why we heat up. So this analemma does define the seasons. It even tells us, see that one point in the middle of the figure 8? What do you think that is? Those of the two equinoxes. It's actually the same point. And it's where the Earth and the Sun sort of balance out, and that's when you get closest to a 12-hour day and closest to a 12-hour night. Here in Earth, do we get a perfect 12-12 split? No, because we're north of the equator by a lot. We're at 40 degrees or a little bit more north of the equator. So we got like 12 and a half hours of one and 12 or 11 and a half of the other. So while we're talking about equinoxes and solstices, the Native Americans who lived here were obviously very interested in that, tracked it very carefully, and built amazing structures. Has anyone ever been to Chichen Itza? Oh, do you have stories? Anything you want to share?
Yeah, I asked the Mayan if the world could end in 2012, and he said, "You're crazy."
Good, thank you. Has anyone been to Machu Picchu? All right, stories there? I envy you, because I have not yet been there. So this is a Pawnee star chart. This is from the Skeety tribe, or Skeety band. And you can actually see how they were marking out constellations. And of course, we've got the Lakota constellations here. And I'm not enough of an expert, we don't have enough time to compare the two. But you'll see some similarities as well as some differences, because of course every culture around the world had their own star stories. They saw different things and they interpreted different things. And Suzanne, you've got to tell me about Newgrange too.
Well, they started with an altar up on the top of a hill, and then they started building stones around it until they got this huge mound. And they had this long passageway that on December 21, the sun goes right down to the altar. And it's quite a walk from the outside to the altar.
So think of the engineering involved to make sure that a shaft of sunlight penetrated just the right way on just that day and at that time. And what sort of rituals and stories surrounded all of that. And then look at these enormous rocks. These are called megaliths because they're huge. We're talking hundreds or thousands of pounds for each rock that they dragged into place and then carved. And these swirly things actually indicate sun and other astronomical objects in the sky. And so if we go inside the tomb, I don't have a picture, unfortunately, but I have a map. And this is sort of what it looks like in there. And the amazing thing is this structure is older than the pyramids in Egypt. And they had rooms telling you what would happen at different seasons, what would happen throughout the year. I mean, incredibly complex. That would be a whole nother talk, just talking about Newgrange tomb. Anything else from anyone else who's been there?
For people who don't know where it is, it's about 40 miles north of Dublin.
Please put that in your itinerary if you ever get a chance to go to Ireland.
And it is older than Stonehenge.
It is. It's ancient. To my knowledge, this is actually the oldest human-made observatory or astronomical-based site. Because if it's older than the pyramids, I mean, there might be some places in China and India that are older, but I'm not aware of them. After about 5,000 years ago, a record starts to run out. So this is ancient. Well, let's get back to some basics. Let's talk about what happens at the solstice. And for that, I need 2 volunteers, please. Can I have 2 young? Oh, yes, please. And I need another young person. Oh, fantastic. Excellent. All right. Thank you very much. All right. Well, first I'm going to have you do 2 different things. I want you to step about 2 feet away from each other. And your name is?
Ariel.
Ariel. Thank you. And you are?
Emma.
Emma. Fantastic. Are you sisters?
No.
You're friends. Even better. Sisters argue. I have 2 girls. They argue all the time. That's great. Well, the first thing I want you to do is I would like you to face each other. And Emma, I would like you to curtsy, please. Do you know how to curtsy? Okay, so please curtsy. Excellent. And Ariel, can you please bow? Okay, now, I want you to bow and hold the pose, please. Okay, stop. Do you see the angle she's making with her back? Now, why don't you go ahead and have your arm down, because that's going to hurt. Can you bend all the way down so that you're really sort of sticking? There we go. See how this is sort of what we call a 90-degree angle? Now, can you come up a little bit? Now, if I would put my arm parallel, which I'm doing, to her back, what angle do you think that is? So can you come up a little bit more? And a little bit more? Stop right there. Do you think? I'm trying to get you to match what I have there for the Earth. Which way should Ariel go?
Down.
Down a little bit? I don't know if I can get you to 23.5. Okay, good. Stop. You're good. You're good. Yay. Thank you. All right, hold that pose. So Earth bows too. That's what we call Earth's tilt. That's okay. You don't have to hold it. That hurts your back. So stay here. I still need you guys. So Earth bows toward the sun. That's what we call the tilt of Earth. Now, you get to be the sun. So spread out all that good sunshiny goodness. All right. Ariel, please bow 23.5 degrees or so. Okay, and stop. Now, what's happening to the top of Ariel's head? Is Ariel getting a lot of good sunshiny goodness at the top of her head? Yeah, so what season do we call this? All right, and that is why it's the longest day of the year. The sun's rays are most direct and most intense right here at the North Pole, because this is the North Hemisphere we're talking about. Now, here's the hard part. Stand up straight, please. You're still the sun. You're still giving out good glowy goodness. Do you want to be Earth now? Okay, guys, straight places. All right, so now Ariel is the glowy Earth. Now, here's what you have to do, Ariel. Emma, excuse me. This is the hard part. You have to lean back. Lean back, lean back. Is that about 23? Oh, perfect. Excellent. Now, where is the good glow hitting? The top of Emma's head? Where's it hitting?
Belly button.
Belly button. Maybe the bottom of your chin. Is that a comfortable position? No, you're not going to hold it very long, so stand up, please. Okay, so this is why, whoops, I got ahead of myself. So this is why when it's winter solstice, we have the shortest day of the year. Because, yeah, you're getting sunlight, the same amount of sunlight, but it's not here where it used to be. Now it's belly button and other places that are getting all warmed up. But not your northern hemisphere. And if anything does hit, it's not that direct. It's kind of weak. All right, so thank you very much. Have a seat. So I did get a thank you. If I said Earth is not closest to the sun at the summer solstice, because it's not, when is it closest to the sun? Actually, that's not true. But Earth is a little closer to the sun then. Do you know when it's really closest to the sun? Oh, you're raising your hand, John.
January 10th or so?
January 4th or 5th, or thereabouts, yeah. So when are we furthest away from the sun? In the summer, but do you know when? 4th of July. Actually, this year it's going to be 5th of July, but normally it is 4th of July. So when you're out there at your summer barbecue and you're sweating and your Earth is farther away from the sun. So it's not distance or closeness to the sun that gives us those hot days or those cold winter days. It's how much we bow. It's how much we tilt. Anybody have questions or comments? Okay then. So let's get back to calendars and how it used to be done in the old days. Not only did people track the seasons, and in fact, summer is actually technically going to start at 5:08 p.m. Mountain Daylight Time on June 20th, to be specific. But if you're Celtic, anyone here of Celtic origin? Then you'd celebrate, you're going to have to help me pronounce things. You'd celebrate Litha, which is the summer solstice festival. But you don't go straight then to the fall equinox. There's something in between called Lammas, or actually, I have no idea how to say this. Do you? Okay, I'm good with that. And that was to honor the Celtic god of many skills, and that's when you gather berries, the summer berries. berries ripen at that time, and your first harvest of summer wheat. And then when we get past fall equinox, yeah, then we're into Samhain. What's that?
Soet is the correct pronunciation.
Oh, thank you, because I don't know these things. Of course, El Dia de los Muertos, or Halloween, we celebrate dead things and reuniting with loved ones who have passed on. And then, of course, once you get past the winter solstice, you're into one of my favorites. And that is Punxsutawney Phil. So you see, it's really important to be able to track not just when the equinoxes are and when the solstices are, but those exact points in between have meaning also to humans. And every culture has some way of celebrating these. So for instance, that's why May Day is such a big deal, because it's halfway between Easter and the summer solstice. So let's get into actual timekeeping. And I want everyone to nod your head, please. Everyone. Okay, you may stop. Thank you. That was you nodding. So synodic time is the time that's important to you. It's what you as a person see and care about. So if there are going to be conjunctions, if you're going to see the moon and Venus at a certain place at a certain time, that's important to you. It actually comes from the word synod, like an ecclesiastical synod, when a church decides to gather its elders or its people to have a big annual meeting and vote or whatever. Well, of course, this is also old. This is from 2,300 years ago, a place in Peru called Chanquillo, although I'm probably butchering that. Does that sound right?
Chanquillo.
Thank you. And so what they had was a 2,300-year-old solar observatory. So this was the June solstice, the equinox, the December solstice. This is where the sun is. And you'd look for when the sun would rise to the right or to the left or the exact center of one of these, and you'd know what day it is. It's actually such a good calendar that even though it's 2,300 years later, it's still good to within about 3 days. And then, of course, you come back again. Notice there's only one equinox point because there only needs to be. So this was their version of the analemma calendar. But then there's sidereal time, what the actual objects in the sky are doing. And that's the real star time. And so it comes from the word sidus, sidereal, meaning star. There's also the word stella for star, where we get constellation. Anywhere, the stellar, right? Anything that has stell or side in it means pertaining to stars. But really, we're not paying attention to the stars. We're paying attention to what is happening on Earth, and specifically how Earth moves. So when we try to figure out where things are on Earth, or where things are in the sky, we want to know where's the where's the equator? Well, we've got our own equators. We've got the equator on Earth. We can extend that out to a celestial equator. We know where the North Pole is on Earth, so that's the North Celestial Pole. Same with the South Celestial Pole. And then we make this imaginary line called the meridian. So you take your arm, you hold it out straight, parallel to the ground. You're welcome to do this with me. So now you're parallel to the horizon. And when you go outside, you can do this too. And if you want to find out where a star is, you just raise your hand. Well, that's your meridian. And your fingertips are going to point to a star. And it could go directly overhead even. That's the zenith point. So anywhere between the zenith and the horizon, somewhere along that meridian, you're going to see a star. Okay, arms down, please. And so you follow that star. Actually, I don't know if you can do this without hitting people. So this is why I wanted your arms down. So I'll do it for you. So you've got your arm up, and then you want to follow it to the right, because it's going to move across the sky. And so we say it ascends. It gets bigger. It goes across the sky to the right. So that's right ascension. That's how we figure out longitude on Earth, and the equivalent of longitude, right ascension, in the sky. So if we want to find where a star is, we need its geographic coordinates. On Earth, that'd be longitude and latitude. And in the sky, it's right ascension and declination. And that's how we figure out, okay, real astronomers can correct me on this, but that's pretty much how it works. So if you keep your eye on that one particular star, now you've got a whole clock of the sky. Because for you to start here and go all the way around in a circle, you've just done one complete rotation of Earth around its spin axis. One spin by Earth on its spin axis will get you pointing right to that same star. Do you have a question? No? Okay. Does anybody have a question on that? That's tricky. Does anyone have a correction? Okay. So believe it or not, for a while there was a gentleman making a sidereal time clock. I would have loved one of these 24-hour clocks. Except that it's not 24 hours. It turns out that for Earth to spin once on its spin axis is 23 hours, 56 minutes, and 4 seconds. That's not what we learned in school, is it? So sidereal time and synodic time are off from each other. Well, so how about modern calendars? Do we fix it? Not really. Why do we have a 360-degree circle? Does anybody know? Well, how many days do we have in a year? Right. So if you're off by a little bit, hey, you got 360 degrees. So for us to circle once around the sun, it's about 360. That's an easier number to do math with than 365. So that's where it comes from. And it was the ancient Babylonians who did that. And they had a thing for the number 60 anyway. So that's why we have 60 minutes in an hour and 60 seconds in a minute. Thank you, ancient Babylonians. It was the ancient Egyptians who gave us that roughly 24-hour day. And let's get back to moon phases. If you're in ancient Egypt, you had several different Abrahamic faiths come through, right? So Jews had their own calendar based on moon phases, but they realized they needed corrections to keep the spring holidays actually in the season of spring. Then the Christians came and developed their own calendars. And then in Islam, there was the sense of, well, we still want to keep the lunar calendar. The Christians had gotten rid of that. But in the Islamic faith, they brought it back, but they said, we don't want to have these corrections. We're just going to go straight through. So it turns out their calendar only has 354 days, and that's why the festival of Ramadan actually migrates all through the year. It was originally based, I think, in the spring, but it now migrates through the entire year. So depending on your culture and your cultural preferences, your calendar can be whatever you want it to be. And of course, the Catholic Church had some very, very specific ideas. And that's how we got our modern calendars based first, the Julian calendars, Julius Caesar, right? See that? And then Pope Gregory, about 500 years ago, ordered a calendar overhaul. And so they came up with the idea of leap days. It's still wrong, but it's better. And that's why every 4 years we celebrate a leap day. And we just had one this February 29. So modern calendars acknowledge that there's a disconnect between what Earth is really doing and what we want Earth to do when we develop months. And even our months are not consistent. February only has 28 days normally, except for this year it had 29. And then some months have 30 and some have 31. And I don't know where that comes from. Because if you're doing a synodic month, you only have 29 days. So it's like, what? Where did the 30 and the 31 come from? So we add stuff. And when it comes to time zones, oh my. For one thing, all of China is one time zone. For another, has anyone been to Indiana recently? What time is it there? Exactly, because they don't do daylight standard or daylight savings time.
They do now.
They do now? Oh, good.
A couple of years ago.
Oh, thank you.
Arizona still does it.
Oh, okay.
Arizona and Hawaii don't.
Okay. Well, check out Nova Scotia. Nova Scotia here is 3.5, so it's a half hour off. Which is actually better than this place in Bangladesh, which is 5 3/4. Okay, go.
I used to have people that work for me in India, and they're in half hour
about something. I'm from Argentina, and Argentina has a very colorful story. We even, Argentina has had too many military revolutions and coups and stuff like that. We once actually had revolutionary time instead of daylight time savings. We literally had revolutionary time, and for years the country was on whatever was that revolutionary time. But then there was change on the government's democracy and whatnot, and say it's time to go back to the right time based on the distance from Greenwich. And it just happened that someone, said, hey, you know what? Many other countries are doing these daylight time saving things. Maybe it's a good thing. Maybe we should try it to save energy. Good. What they didn't realize was they were looking at countries in Europe and the US that are on the northern hemisphere. Argentina is in the southern hemisphere.
This is Argentina.
Yeah, thank you for pointing where. So what actually happened was that they implemented daylight time savings the wrong way. So Argentina is wide enough as to have 2 time zones, but most people live on the east part of the country. So the whole country is shifted, or the west part of the country is shifted always 1 hour because of that population thing. When they did that small thing of, okay, let's change daylight time savings, and they did it the wrong way, what happened was that the west part of the country ended up 3 hours off. You ever heard of the midnight sun? It was here all the time for a long summer. I thought of adding that.
Thank you. Thank you. I congratulate you for surviving revolutionary time and so, yeah, time zones are what we make them, not really based on any actual physical reality. And then, of course, yes, go ahead and blame the railways, because that whole, what's that line about the timetable for the train is always right? Right? Well, that's where that came from. And so we got even further shifted away. So local noon, whenever the sun was actually the highest in the sky, that's not when you go for lunch. You go for lunch when your watch says 12 or 11 or whatever, because you're following whatever the timetable is, not what's actually going on. Well, when we started developing satellite technology more than 50 years ago, we realized a few things. First off, satellites can keep really precise time, or they can help us to do that. And as we developed computer technology and infrastructure, that really precise timing was important for information sent over these brand new things called the internet and the World Wide Web. And so maybe mapping the Earth would be a good idea. Now, we've been mapping the Earth in all sorts of ways for forever. But now we needed to map the Earth using satellites and then having it tell us where we are. So how many of you have a GPS unit in your car? Yeah, that's Global Positioning Satellite System, GPS. That's the GPS system. And what that does is it helps you figure out where you are. There's just one problem. Earth is lumpy. It's not a perfect sphere. And it's got what are called mass cons. We actually developed that were in the early 1960s when we started investigating the moon, and then we realized, wait, Earth has mass cons too, and they don't make any sense. So we're still trying to figure out geologically why some things are more massive than others, because it doesn't look like that on the surface. So got some issues there. So it turns out that mapping the Earth is really important. Well, how about what do we do now? I mean, we should be so modern, right? I don't know if any of you noticed, but the entire country of Samoa skipped an entire day a few months ago. They had been over here in terms, if this was the international dateline, here's Samoa. But they wanted it to wiggle around them so that Samoa would not be in the same time zone as American Samoa. They didn't want their trade relations with the U.S. to dominate everything, because most of their money is actually from trading with Australia and Japan and other places in between. So they wanted to be in pretty much the same day. And the whole thing about the international dateline day. If you're on the other side, you're on another day. And that makes trading really hard. So they just decided they're going to skip a day, which they did. You can still do that. So calendars and clocks are getting increasingly static. We're getting more and more disconnected from what's really happening. And we're getting more and more emphasis on different ways of telling time. So you can actually go to, when was the modern clock invented? It was actually only 300 years ago. John Harrison in England. And from that we were developed the modern longitude system. And that helped us enormously with right ascension. Well, so now we use atomic clocks. And has anyone seen the atomic clock at NIST in Boulder? No? Can you tell us? You used to work there, so did you ever work with the atomic clock?
Not directly, no.
Was there just one?
No. There's 9.
That's right, there are 9 of them. So, Mike, I'm going to ask my lovely assistant, Mike. He's my husband. Thank you, Mike.
Oh, me.
Yes, you. Would you please stop the PowerPoint and put on that BBC, that's right, and then get it on full screen? And we're going to let a lovely lady from the BBC tell us all about this.
The Earth's rotation to measure time. And we did that by looking at the stars at places like the historic Royal Observatory at Greenwich in London. But astronomy no longer cuts it when it comes to counting the seconds.
Well, by the 1950s, it was realised that the Earth itself isn't a perfect timekeeper. It speeds up and slows down unpredictably in its rotation.
So, scientists came up with a solution, the atomic clock. These clocks use the tiny but very regular changes in cesium atoms.
Well, any sort of clock has to be based on some form of oscillation that repeats regularly over time. So in a traditional pendulum clock, you have the swinging pendulum to keep track of time. And an atomic clock is the oscillations of the atoms.
So what exactly is the definition for the second?
At the moment, the second is based on one particular resonance in cesium atoms. The atoms give out a frequency which is precisely 9,192,631,770 oscillations per second.
Atomic clocks only.
Okay, so that was nearly 10 billion back and forth movements every second. And that defines a second if you're using an atomic clock. Do we know why? Oh, can you start that again, please?
I think it's still loading.
Oh, that might be the issue. That's okay, it does that. Just back it up a couple of seconds. There we go. And start it again. Okay, or not. Okay, this might be a good time for me to take questions. So,
Do it.
that's okay. So while it's loading,
It's loading time.
it's loading time. See, we also live our lives according to how long it takes the computer to download the data.
I think MBS can keep time tacked at 1 part 10 to the 17th.
Yeah, it turns out that these atomic clocks are actually getting obsolete. And we're now developing technology called optical clocks. Do you know about that?
I've heard about it, don't know much about it.
Okay, well, tell me what you do know.
I don't know nothing about that. I just know that it's a lot more accurate.
Right, so the cesium atom, we count it vibrating back and forth, or actually I should say again for my Astronomy 101 students, it's a particular electron transition from one energy level to another. And it's not n equals 1 near the nucleus, it's far away. It's just bouncing back and forth and back and forth. And if it's nearly 10 billion times per second, that means we can count time to 1/10 billionth of a second. But what if we had a more energetic electron that was vibrating even more? And we couldn't look at it using regular light we see with our eyes. What if we had to look in the ultraviolet? So it's just the same light in a tanning bed. People who go deliberately get tan. I know, who would be that dumb? But anyway, it's that same ultraviolet light that gives you both a sunburn and skin cancer. That one. And if you can look at the electron vibrating that way, you can go into hundredths of a billion or thousandths of a billion. And that's what these optical clocks that are being developed in Boulder and other places are doing. But it's really in Boulder, Colorado that we've got the most accurate optical clock prototypes. We don't
precisely 9,192,631 and 770 oscillations per second.
Atomic clocks only lose 1 second every 30 million years, but just one of them by itself isn't enough.
In fact, there are 350 atomic clocks dotted all around the world. That's because, as precise as any one of them is, there are still tiny variations in the measurements they make. Every single clock has a slightly different time. So, the data from all of these is brought together and averaged out to give us the single most accurate measure of time possible.
And that takes place here at the International Bureau of Weights and Measures on the outskirts of Paris. This is the place by which the world sets its watch. Dr. Felicitas Arias is the director of the world's time. And she says keeping the world in sync is vital for a huge range of things, from the financial markets to sat-nav systems. It's a huge responsibility.
We cannot have a bite at the office. And something that is very curious is that if we make a mistake on the time scale, we cannot go back to the past and repair the error.
But the story of time doesn't end here. Scientists are now working on the next generation of timekeepers. They're called optical clocks, and they're so precise that they'll only lose a single second over the entire age of the universe. Rebecca Morrell, BBC News.
Okay, thank you. So if you can please go back to the PowerPoint.
I have a question.
Yes.
I know the atomic clocks in Boulder, but there's these red reflectors up in Wellington. What is the purpose of those? Because people keep saying they're atomic clocks, and I said, no, it's in Boulder. What is the connection between the two? It's a series of standing red lights that blink.
That isn't related to the atomic clock, but does anyone know, please?
I believe they're slave to the clocks in Boulder, and then they broadcast that all over the country for synchronization.
Well, Fort Collins has a broadcast WWB, and you can receive it on shortwave, 5 megahertz, 10 megahertz, 15, 20, 25. And they have four atomic clocks I think are in Boulder, and 5 are in Fort Collins. You separate them so you can't destroy them all at once. And they're intercompared daily to do that special average, which comes out to be the accurate time. The problem is that clock is so accurate that the sidereal time begins to slip, and so you get leap seconds once or twice a year.
We're getting
bring
there.
the clocks back into phase.
Yes, we're getting there. Thank you both very much. Please.
You know, when they were talking about that optical clock, they said this uses a second in the life or the time.
Oh, loses as in gets out of phase. The sidereal time and the synodic time. Again, because Earth has natural movements and motions. Every time we have a really big earthquake, or when we have a really big volcanic eruption, the mass of the Earth actually shifts, and that means the way it rotates changes. And we can actually slow down Earth's spin rate with one really big earthquake by 3 billionths of a second per year. That's actually a significant amount, especially if you're doing satellite timing, right? So Earth is an unreliable timekeeper because it stops and starts and spins in weird ways and changes its mass. It's a normal planet. But it means if you're trying to do really accurate timekeeping, you want to do something synodic, like an atomic or an optical clock. And then you want to get as precise as you can. And even the most precise one we have is still going to lose a second over tens of billions of years. So, yeah, nanoseconds matter because of the stock market more than anything else. Billions of dollars ride on being able to be just 1 nanosecond faster than somebody else's trade to buy or sell or, make the stock this amount or that amount. And of course, defense cares about it as well. So the master clock for the U.S. Naval Observatory is what's pictured here. That's in Washington, D.C., but the backup is right here in Colorado at Schriever Air Force Base outside Colorado Springs. Again, Colorado is crucial for timekeeping in the US, between the atomic clock and the master clocks. Big deal. But as I said, earthquakes and even tides, which is the gravitational pull not only of the moon, but also of the sun on Earth, they can affect Earth's rotation rates. So we just heard people talk about how you officially keep time, and I'm not going to get into that tonight, but obviously I can send you for more reading. So yeah, let's talk about that leap second idea. It was introduced in 1972 because by that point we had enough satellites and we had enough financial transactions that depended on what information was being sent through the internet. World Wide Web didn't exist yet, but we did have enough that this discrepancy was literally costing people money. And so we introduced this idea of adding a leap second every once in a while so that it's not as big a deal as adding a leap day, but it makes these little adjustments. In January of this year, the International Telecommunications Union, which is an office of an office of an office associated with the UN, these are the guys that control all of our telecommunications, meaning all of our TV, all of our radio, everything that basically we use to communicate with each other. We're so dependent on our satellites, the satellites get messed up whenever Earth changes what time it is. So the Americans, the French said, you know what, let's get rid of this leap second because it messes up our satellites all the time. Let's go do something else. And I'm not going to get into what they proposed. England, of course, they are the ones that have Greenwich Mean Time running right through them, right? Because Greenwich, England, that defines. Remember I said the meridian before was that important line of tracking the star? Well, the prime meridian is how, it's our 0 point for longitude, and it's also the 0 point for when you start clocks in the olden days before atomic clocks. That's a huge deal. And they said, no, we have to keep the leap second. We have to keep our current timekeeping system. There was this huge argument. And you know what they decided? To not make a decision. So our next leap second will be on Jupiter. Okay, so here's the real resolution, and this is actually, I'm getting very close to the end here. Mike, do you mind going ahead and playing that other video, please?
Let's see if I can get this one loose.
That's okay.
Back here.
It'll be a little easier because it's a 2-minute video. Yep, that one right there. So here's the real solution. Yeah, just play it this way. It doesn't have to be full screen.
Well, it's not buffered. It's likely to stall.
Oh, well then, do you want to reload it?
Just going to refresh.
Okay, go ahead and refresh. I'll talk in the meantime. So here's the thing. There was a spacecraft called Gravity Probe B that took so many years to develop that many of the astronauts in the U.S. space program got their PhDs from this program. It was first proposed in the mid-1960s. It finally launched in 2004. And took data for over a year. Then it took them years to analyze the data. And Mike, do you think we can play it, or should we let it?
It seems to be stalling at the same place. I'll play as much as I can.
Okay.
A space-time vortex around Earth, presented by Science at NASA. Would you believe Earth sits in the middle of a space-time vortex? Einstein predicted this almost 100 years ago, and it turns out to be true. On May 4th, 2011, researchers announced that NASA's Gravity Probe B spacecraft has detected the vortex, and its shape precisely matches the predictions of Einstein's theory of gravity. The space-time around Earth appears to be distorted, just as general relativity predicts, says Stanford University physicist Francis Everett, principal investigator of the Gravity Probe B mission. Time and space, according to Einstein's theories of relativity, are woven together, forming a four-dimensional fabric called space-time. The mass of Earth dimples this fabric, much like a person sitting in the middle of a trampoline. If Earth were stationary, that would be the end of the story. But our planet spins, and the spin should pull the dimple around in a four-dimensional swirl. This is what Gravity Probe B went into space in 2004 to check it. The idea behind the experiment is simple. Imagine trying to spin a toy top on the dimpled surface of that trampoline. It's going to wobble, right? Something similar happens when you try to spin a gyroscope in curved space-time. Its spin axis will drift or precess. Gravity Probe B carried some super-spherical gyros into Earth's orbit to see what they would do. In practice, this simple idea is extremely difficult. According to calculations, the twisted space-time around Earth should cause the axis of the gyros to drift by a tiny amount. Really tiny. It's like measuring the thickness of a sheet of paper held edge-on 100 miles away. Even the slightest disturbance could ruin the experiment. We had to invent whole new technologies to make this possible, says Everett. The Gravity Probe B team developed a drag-free satellite that can brush against Earth's atmosphere without disturbing the gyros. They figured out how to keep Earth's magnetic field from penetrating the spacecraft. And they created a device to measure the spin of a gyro without touching the gyro. Pulling off the experiment was a big challenge, but after a year of data taking and nearly 5 years of analysis, the Gravity Probe B scientists appear to have done it. The gyro is precessed, the vortex is real, and we are in it. Einstein was right again. For more information about the space-time vortex and what it means to us on Earth, please visit science.nasa.gov.
Thank you, dear. And back to the PowerPoint. It's okay. And we're done with videos. And we're almost done with the talks, too. So here's what it really boils down to. I've been talking about how, it doesn't matter what Earth does, we're getting far away from it, except that time itself is not isolated. It's actually part of this larger fabric called space-time. And instead of thinking about it like a trampoline, think about it like a Jell-O mold, one of those Jell-O salads, right, with the pineapple chunks and the marshmallows in there. And imagine your little marshmallows were spinning, moving, and what would happen to the Jell-O once the little marshmallow spun away inside it? It's still inside the Jell-O, but what would the Jell-O itself do? It sort of ooze in and fill in the gap, and so space-time forgets that you were there because now you're over here. So space-time itself is like that Jell-O salad thing. And if you look at my dress, I don't know how well you guys can see it in the back. I deliberately wore a really swirly dress. So I'm going to swirl. What's my dress doing? It's swirling. Well, guess what? As Earth spins, it drags the fabric of space-time with it, just like my skirt. So we can't divorce what Earth is doing because Earth's dragging time. So that's why it gets really complicated to answer that simple question. What time is it? Well, I don't know. What time is it? Is it synodic? Is it sidereal? Are we worrying about space-time swirl? So astronomers have always measured how we keep track of time, whether it's minutes, hours, months, days, years, seasons, decades, millennia, doesn't matter. And the actual shape of things, whether they're planets or other objects, they're important too. Lives and money depend on getting as much accurate information as we can. So that's why we're always building better clocks, we're always building better satellites and getting a better idea of the real shape of things and how these things move and interact with each other. So this is a story in progress. And I want to thank you. Did you have a question? No? Anybody here? Question. Thanks.
Not so much a question as back to your earlier point, according to Scientific American's website, the Japan earthquake slowed the rotation of the Earth down by 1.8 microseconds.
Thank you. And a microsecond is a millionth of a second, so that's actually a big number compared to a nanosecond, which is a billion. Micro is 1,000 times bigger than nano. That's a lot. Thank you. Other comments or questions? Yeah?
There's a number for the effect, especially
Okay, but they didn't really. Can anyone other than me explain what really happened? Pablo, come on up. Go for it.
So, I think it was 6 months ago or something like that, there was an announcement made about a kind of particle that is called a neutrino. And what they were doing on that experiment is they were creating the neutrinos in Switzerland and send them underground through Europe and detecting them, measuring the arrival of them in Italy. And they were knowing, okay, this is the distance, this is the speed of light, and they were just going through all those experiments and measuring the time, and it seemed like the neutrinos were arriving there faster than the speed of light. So that is like, you know, when there is a lightning or a lightning bolt that you see the light and then you hear it, it will be the other way around, that you hear it first and then you see it. That's what they were suspecting. Those scientists were really confused by that, and they said, well, we don't really understand this, but this is what we're seeing. They made that announcement. And there was a lot of excitement. It was like, oh wow, Einstein was wrong. You know, it could be a portal to other universes. People went crazy on all that those things. Myself and most scientists felt there is something wrong on the experiment. No one knew exactly where, but it was like there is something wrong on the experiments. There were other evidence, and if someone wants, I can talk offline about that, to believe that neutrinos move at the speed of light or slower. And yeah, about 6 months later, it was confirmed that there was a problem on the experiment. These experiments are extremely complex. There were some pictures, some slides here showing the atomic clock and all that, the hardware and all those racks and things like that. These experiments have probably rooms that are 10 times the size of this room, full of computers and equipments and cables and things like that. It was just a mistake. There was literally a loose connector. And it just takes a lot of time to go through literally millions of cables and connectors to figure out what the problem was. They probably should have found it sooner than they made the release, but oh well, that's life. So you guys can, rest. Einstein is still right, nothing moves faster than the speed of light that we know of.
All right, thank you. So the reason I wanted Pablo to answer this is we have to tie in things to reality, all right? Loose cables. How long does it take for the electrons to flow from this part of the cable to that part of the cable? If we're sending a signal to a satellite and then back down again, how long does it take for that signal to bounce, to go up and then down again? So all of this has to be taken into account. And so, yeah, when we're trying to do general relativity or special relativity versus our ordinary time, I'll put that in quotes, really what you're doing is you're just accounting for all these different things that could potentially affect the measurement you get.
If you don't mind, I just want to share a little bit of something you said, and I bet, Mike, in the back, you're going to relate to this. Back when I was doing nuclear physics in my laboratory, I will have a lot of cables on the rack that we use to connect different equipment to. My cables were not sorted by length, but by the time that the signal will move through the electron. I bet that you've done that too. So a cable, you wouldn't, I see Mike saying yes, a cable wouldn't be 3 feet long. A cable will be a 9 nanosecond cable. Or this one that maybe got bent and you recalibrated, it will be a 9.5 nanoseconds. That is the kind of reality that you deal with. Cables are measured or are sorted by the time that an electron, it's not really the electron, it's the electromagnetic signal, moves through it from one end to the other, and then you need to take into account that there are connectors at the end, and those also add some time, and the list keeps going and going and going. So keeping track of time is incredibly tough.
this